Hi students, today we will see the properties of aryl halides. We already studied about the aryl halides properties, that is electrophilic substitution reactions, and second one is reaction with metals we studied. Now we will study about the nucleophilic substitution reactions. Here generally a nucleophilic substitution reaction means here this is aryl halide or haloarenes. It is reacting with a nucleophile, and by the nucleophile reaction it is giving a compound like nucleophile is present and halide ion is released. This is called as simply nucleophilic substitution reactions. But in this nucleophilic substitution reactions, if you see, very important thing is alkyl halides. We have already studied this alkyl halides. Alkyl halides are much more reactive than aryl halides. Alkyl halides are much more reactive than aryl halides towards nucleophilic substitution reactions. We studied SN1, SN2, SN reactions now. So alkyl halide shows that nucleophilic substitution reactions more readily than aryl halides. Why? Why alkyl halides show more reactivity and why aryl halides are less reactive? Why aryl halides are having less reactivity towards nucleophilic substitution reactions? So in this, if the reasons are taken, in this first one is resonance. The first reason we can say that is resonance, and second reason is bond length. The second reason is bond length, and third one is stability of carbocation formed. The stability of carbocation formed. And the next one is fourth one. Here the groups present. The groups present on benzene ring. Present on benzene will influence the reactivity. So the groups present on benzene, we can say, will influence the reactivity. So these are the reasons we can consider to explain about the alkyl halides more reactivity and aryl halides less reactivity. Okay, we will check it one by one. First reason or the first cause why aryl halides are less reactive in this first cause is resonance. Here we are telling resonance. What is this resonance? For example, if you are taking an aryl halide, this is an aryl halide, and in this aryl halide, if you are having, for example, chlorobenzene is taken. So this is having 3 lone pairs on it, and these lone pairs and the pi bond are in conjugation. When there is a conjugation, what happens? If there is a conjugation, generally there is a resonance, and because of this resonance, it gives the lone pair to the benzene ring, and so this pair of electrons shifts onto the adjacent carbon atom. So because of this, you will get a resonance structure. So this is the resonance structure possible. Here this is negative charged now having a lone pair and pi bond, and now it is becoming a Cl double bond, and it has now 2 lone pairs only. There is a positive charge on it. Okay, and this pair of electrons are shifting because of this pi bond shift. Here this pair of electrons shifts onto the adjacent bond, and then this pi bond electron shifts onto the adjacent carbon. Please remember, this lone pair shifts onto the adjacent bond, and the pi bond shifts onto the adjacent carbon atom, not to the adjacent bond. While writing the arrows also, please write carefully. Okay, next here what is formed is, then we are getting double bond Cl, no change. Here 2 lone pairs and positive charge, and now we are getting a pi bond here, and here there is a lone pair negative charge, and here there is a pi bond. and now again this electron shifts onto the adjacent bond and this pi bond shifts onto the adjacent carbon atom. Then here the resonance structure possible. Here double bond and Cl having two lone pairs, and here it is positive charge. Okay, and now here there is a negative charge and having a lone pair, and this is a pi bond and this is another pi bond. Okay, now what happens is these pi bond electrons or the negative charge electrons are shifting, and these pi bond electrons are shifting onto the chlorine atom. Now what we can write is here, see, this pair of electron shift occurred, then the structure possible is here, this is the structure, pi bond, here pi bond, here pi bond. Here there is a chlorine atom only. This contains now 3 lone pairs. So if you see in total number of resonance structures, 3 resonance structures are having a carbon chlorine double bond. So we can say due to resonance what happens? Due to resonance mainly what happens means carbon chlorine gets partial double bond nature. Partial double bond nature. Partial double bond nature. So what happens? When there is a single bond that requires less energy to break, when there is a double bond, single bond is there. For example, CCl single bond is there and C double bond Cl is there, which can be easily broken. Single bond, this requires less energy, but this requires more energy. So this is requiring less energy, whereas this is requiring more energy. So that is simply, so this bond dissociation is not easy. Whereas in alkyl halides, there is no such type of partial double bond character. So aryl halides in aryl halides, due to the partial double bond nature, why this partial double bond nature is occurring? Because of resonance. Due to resonance, it is getting a partial double bond nature, so it is having more bond strength, and so it is not easily participating in nucleophilic substitution reactions. This is first example or first reason for not showing more reactivity towards nucleophilic substitution reactions. Second one, bond lengths. So second one, if you are taking bond lengths, what is this bond lengths? Here if you are taking an alkyl halide and aryl halide, suppose if it is alkyl halide, here it may contains X, H, H, and there is another alkyl group or whatever it may be. This is alkyl halide. Okay, it is a primary alkyl halide, whatever it may be. And I am taking aryl halide. Here, this is aryl halide. Aryl halide means benzene ring is present now. This is the benzene ring, and here double bond, double bond, double bond, and here there is a X. Here, what is the carbon atom? Please tell me. Here, this is sp2 carbon, and this is sp3 carbon. Alkyl halide means sp3 carbon. So whenever we are taking the bond length values, sp3 carbon and sp2 carbon, then check the bond length values. Here, this is having 1.77 angstrom minutes, and here this is 1.69 angstrom minutes. Okay, so please see the bond length values. The bond length values of this CX bonds. Here, what we say bond length means CX bond length values. So whenever CX bond length values of alkyl halide, and this is aryl halide. So this is alkyl halide, it is alkyl halide, and this is aryl halide. So when aryl halide and alkyl halide CX bond lengths if you check, then this is having more bond length. When bond length is more, what happen? Bond energy decreases. So we have a relation bond length inversely proportional to bond energy. Bond length is inversely proportional to bond energy. So when bond length is more, bond energy is less. Easily dissociating CX bond, whereas in this bond length is less, so bond energy is more. It requires more energy. So because of this, the bond lengths, because of this change in bond lengths or difference in bond lengths, the aryl halides are not easily dissociating. The CX bond is not easily dissociating, whereas in alkyl halides, CX bond dissociation occurs easily and they undergoes to nucleophilic substitution reaction easily. But aryl halides not undergoing to nucleophilic substitution easily. Next point, third point, stability of carbocation. The stability of carbocation. The stability of carbocation. Here in the stability of carbocation, suppose we are taking a aryl halide. Aryl halide means this is for example aryl halide, halogen, and alkyl halide also. Here alkyl halide means for example RCH2X is taken. Then if it is losing the halogen, then this pair of electrons are taken up by this, and here also if it is losing this pair of electrons taken up by this, it is forming a carbocation. Here this is pi bond, and now it is getting positive charge. This is called as phenyl cation or phenyl carbocation. And here you are getting after minus X release, you are getting RCH2 plus. This is called as alkyl carbocation. Alkyl carbocation. So if you check this phenyl cation and alkyl cation, which is more stable? First of all, very important is here how many sigma bonds are present? 2 sigma bonds. 2 sigma bonds means it is looking like sp2 hybridized carbon atom. But sp means generally what is the structure? What is the geometry? Linear. But here what is having bent shape or angular shape. If it is having angular shape, it has high bond angle strain, and here positive charge present on the sp carbon atom, so it is highly unstable. So this is a highly unstable because it is having bond angle strain and it is having positive charge on highly electronegative carbon atom because of two reasons. Okay, and second, alkyl carbocation. What is the adjacent group? This is a plus I group. Plus I means positive induct effect group, which donates the electron pair. Here it is donating the electron pair and then increases the stability of carbocation. Plus I groups increases the stability of carbocation. But here it is not happening. So phenyl carbocation or phenyl cation, if formed by the nucleophilic substitution reaction, generally first what happens or what is formed means phenyl carbocation formation, or alkyl halides if taken, alkyl carbocation formation. So in phenyl carbocation formation if occurred, what happens? The stability is decreased. So in nucleophilic substitution reactions of aryl halides, you please remember SN1 reactions are completely ruled out. There is a possibility of SN2 reaction. Why SN1 reactions are ruled out means here, because in SN1 reactions, what are the steps? Yes, first step is carbocation formation. So if carbocation is formed, this is unstable. So never try to get instability for any molecule. So SN1 reactions are completely ruled out in nucleophilic substitution reactions of aryl halides. If there is a chance, then they will go for SN2 reactions only, not for SN1 reactions. And second, alkyl carbocations are stable. They are stable. If they are stable, they can convert either in SN1 reaction or in SN2 reaction, they can possible. Okay. Next, here fourth point I said the groups present. Here the groups present. on benzene ring. The groups present on benzene ring. Please remember, electron withdrawing groups if present. Electron withdrawing groups present on benzene ring. On benzene increases reactivity. They increases reactivity. Electron withdrawing groups. What are these electron withdrawing groups? Simply NO2 group or CHO group or COOH group. Okay, so this type of electron withdrawing groups means along with halogen there is NO2 group at ortho position or para position, for example. Then they increase the reactivity. If there is electron donating groups, they decrease because the positive charge formed here, how whenever NO2 is present, the bond breaking easily and then the electron density decreased largely. So the NO2 groups or electron withdrawing groups if present, then the reactivity increases towards nucleophilic substitution reactions. Okay, and next and another important point I'll give here. See, that is like fifth point. In alkyl halides, we set the reactivity order. Please see, this is alkyl halides reactivity order. Alkyl halides reactivity order. What is the reactivity order we gave? Ri, RBr, RCl, and RF. But here in aryl halides, this is quite opposite. Aryl halides reactivity order is, that is C6H5. Please see, that is C6H5. F means fluorobenzene has high reactivity than C6H5Cl than C6H5Br. Because fluorine more electronegative, so the CF bond dissociation occur more easily. Okay, so the aryl halides reactivity order is quite opposite to alkyl halides reactivity order. Some examples we are taking, examples of nucleophilic substitution reactions, that is we can call it as a dose process. Please remember it is like a named reaction, dose process or dose method. In the dose process or dose method, it is an example for nucleophilic substitution reaction. Please remember, example for nucleophilic substitution reaction. In the dose process or this method, what is the process means? Suppose we are taking a chlorobenzene. This chlorobenzene reacts with sodium hydroxide at 623 Kelvin temperature and 300 atmospheres pressure, followed by the acidification. First, what happens in this reaction means it is converted into OH, means phenol is formed. This is chlorobenzene. This is called as chlorobenzene. This is simply called as phenol. Chlorobenzene is converted to phenol first. But because of this acidic hydrogen, again sodium hydroxide reacts. The sodium hydroxide again reacts. So because of this reaction, because of this acidic hydrogen, I said now this hydrogen is acidic hydrogen. So what happens means this is converting into ONA, a salt is formed. This is called as sodium phenoxide. This is known as sodium phenoxide, and this sodium phenoxide again reacts with H plus. We said now this H plus is reacting now and it is undergoing to acidification. By this acidification reaction, here it is now giving OH. Phenol is formed. Okay, so first chlorobenzene reacts with sodium hydroxide at a high temperature 623 Kelvin and 300 atmospheres pressure, followed by acidification. So first, if you remove this for example, then phenol is formed first. This phenol reacts again with sodium hydroxide due to its acidic nature. Acidic proton present, acidic hydrogen is present, and so it is forming sodium phenoxide finally. But if you want phenol, we are doing acidification. So dose process means directly conversion of chlorobenzene to phenol. So this is again phenol. Okay, this is Dawes process. And here Cl is a nucleophile and converted or replaced by OH group. Okay, next. Suppose I am taking chlorine and here we are taking NO2 group. So this is called as a nitro. NO2 group you can take here at para position. Sorry, NO2 group, and here NaOH, and here the temperature used is 443 Kelvin, and here followed by acidification. Means same process will occurs, but what is present? NO2 group is present. Due to the NO2 group, temperature is reduced. Here what? 623, but here 443 Kelvin. So what is the product? Here we are getting OH and here NO2. This is called as paranitrophenol. This is known as paranitrophenol. Paranitrophenol is formed. Okay, next. Here chlorine and here it is NO2 and here also we have NO2. Then here NaOH, but here it is 368 Kelvin temperature is enough, and followed by acidification it is forming OH and this is NO2 and here again NO2. So it is called as orthoparadinitrophenol. We can write orthoparadinitrophenol. This is called as orthoparadinitrophenol. Orthoparadinitrophenol. And okay, so if you see these reactions, the next reaction I am writing, please see here. Here this is chlorine and NO2 is present. Here NO2 is present. Here NO2 is present. This is called as a trinitrochlorobenzene. This is undergoing to reaction with sodium hydroxide, NaOH, and H plus is taken. But here very important is warm, just by warming only. Just by warming the reaction occurs and the product formed here is very important product. Here OH group and here NO2, no change. Here also NO2 group and here also we are getting NO2 group. This is called as a trinitrophenol, or this is simply called as picric acid. Picric acid. Okay, this is called as 2, 4, 6. 2,4,6 trinitrophenol. 2,4,6 trinitrophenol. Trinitrophenol. 2,4,6 trinitrophenol, or this is called as picric acid. So why I wrote separately, or why here only I wrote means to make a comparison in the reactions only. I wrote on same board. So please adjust. Here what is the comparison? Main comparison is here how much temperature? 623 Kelvin. Without any NO2 groups, please see only chlorobenzene. But here what is taken? para-nitrochlorobenzene. Okay, here this is para position, para-nitrochlorobenzene. How much is the temperature? Means one electron withdrawing group is present. What is this NO2 group? Electron withdrawing group. So without any groups, 623. With a one electron withdrawing group, 443. Temperature is reduced. And here, if you are taking, how many are there? Two NO2 groups. And what is the temperature? 368. Much more reduced. So two electron withdrawing groups are present. This is electron withdrawing group, and this is also electron withdrawing group. And in the third reaction, what happens? Here, this is NO2 group, and this is NO2 group, this is NO2 group. What is the required condition? Just warm. By just warming, by taking NaOH and H plus, just warming, it gives trinitrophenol. Means, whenever we are using electron withdrawing groups, there is no need of high temperature. So the reaction conditions will be different when we use electron withdrawing groups. That is most important thing here. And picric acid, please remember the formula and structure. Picric acid, previously they asked which of the following is having a carboxyl group, or which of the following acid doesn't contain carboxyl group. So doesn't contain carboxylic group means picric acid. Picric acid contains OH group only. It is called as acid, but it contains OH group only. It is not having COOH carboxylic group. Okay, so this is a Dawes process. The first one is only called as Dawes process. Please remember, first one is only Dawes process. This is extension for the reaction. Even if you are taking the same reaction at a different condition by maintaining NO2 groups at different temperatures we are getting, that is the use of this reaction. Okay.